आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
In this episode of the podcast series, we are extremely happy and honored to receive a conversation from Professor Dhruba Gupta. He will now be introducing himself and will be sharing his academic journey to the listeners.
I am Professor Dhruba Gupta and my area of research is nuclear astrophysics. Let me brief you about my academic journey. I did my PhD from Saha Institute of Nuclear Physics and carried out my experiments at the BRC TIFR Pelletron facility, Mumbai. My first postdoc was at UNC Chapel Hill and Triangle University's Nuclear Laboratory, North Carolina, United States. My work involved proton-proton scattering experiments using a supersonic gas jet target. My second postdoc was at the Institut de Physique Nucléaire at Orsay in France, involving experiments on unstable nuclei at the Ganil radioactive beam facility. Thereafter, I came back to India and joined as a CSIR pool officer at the Variable Energy Cyclotron Center, Kolkata, working on heavy ion beams. I joined Bose Institute in 2008 and my area of research is nuclear astrophysics.
Professor Gupta now will be thoroughly explaining his area of research.
Let me now tell you briefly about the area of research in simple language. Now, an atom consists of a tiny nucleus containing protons and neutrons with electrons moving around it. The size of a nucleus is about 10,000 times smaller than an atom. Our studies need beams of energetic particles to bombard on target nuclei, inducing nuclear reactions. This required accelerators, and they were developed to explore stable nuclei during 1950s to 1980s. Now, unstable nuclei with extra protons or neutrons, they decay very fast and are not found naturally on Earth. Therefore, they are known as exotic nuclei. These rare isotopes or exotic nuclei can only be produced and studied in the laboratory. With the advent of rare isotope beam facilities, exploration of these nuclei started in the 1990s. Now, nuclear astrophysics is a field at the intersection of nuclear physics and astrophysics, that is studying celestial objects. It seeks to understand the origin of elements in the universe, that is the elements we see around us and make up our bodies, and also how stars evolve during their lifetime. Now, during the formation of the universe 13.8 billion years ago, in the Big Bang, only the lightest elements, hydrogen, helium, along with trace amounts of lithium and beryllium, were formed after a few minutes of the Big Bang. This is known as Big Bang nucleosynthesis. All other elements are formed much later in the stars, where subsequent nuclear processes synthesize heavier nuclei during stellar evolution and in violent events like supernovae. So, nuclear astrophysics essentially tries to figure out where the building blocks of matter come from by examining the nuclear reactions happening inside stars. Now, let me tell you what we are doing at Bose Institute. So, we have been recently working on the Big Bang nucleosynthesis and the cosmological lithium problem. Now, this lithium problem or anomaly of about 3 times between prediction and observation is one of the important unresolved problems in nuclear astrophysics for decades. We studied this by carrying out experiments at the radioactive ion beam facility ISOLD at CERN. All simulations and data analysis were carried out at Bose Institute. We concluded that our present understanding of nuclear physics cannot solve this problem, and it points towards new fundamental physics. The other work that we are involved in is stellar nucleosynthesis and studying the carbon-12 alpha-gamma oxygen-16 radiative capture reaction. Now, this reaction is called the holy grail of nuclear physics, where carbon combines with helium to form oxygen. This is critical for the abundance ratio of carbon to oxygen after the helium burning cycle and is a key input for subsequent stellar evolution. This is the fundamental basis for the evolution of biological life in our universe as well. So, we carried out improved measurements relative to this reaction. So, how nuclear astrophysics is useful for the society?
Professor Gupta will now be talking about the applicable factors by which his research will be beneficial for the society.
Nuclear astrophysics made substantial progress in recent times that involved sophisticated experiments at rare isotope beam facilities around the world. Scientists are now able to study the universe in greater details. This can potentially revolutionize our understanding of the universe, thereby contributing to science education. It also leads to the development of advanced technologies in other fields. Telescopes, satellites, detectors, and data analysis techniques developed for nuclear astrophysics often find applications in medicine, defense, telecommunications, and environmental monitoring. Now, where does India stand globally in this area? At present, there is a worldwide effort into pursuing rare isotope science, where measurements involve cutting-edge experiments with exotic nuclei. Nuclear astrophysics involves a small collaboration of scientists in an experiment as compared to high-energy physics.
We were lucky enough to witness a short account coming from him about the position of India globally in this area of research.
Now, India is collaborating with leading global scientific organizations like CERN, the European Organization for Nuclear Research in Switzerland, and FAIR, the Facility for Antiproton and Ion Research in Darmstadt in Germany. These projects are at the frontiers of science and technology, and its results will have global relevance.
It would be best to hear from Professor Gupta about his contemporaries.
Now, Hans Bethe is widely considered the father of nuclear astrophysics due to his significant contributions to understanding nuclear reactions within stars. So, he got Nobel Prize in Physics in 1967. William Alfred Fowler is also well known for his theoretical and experimental studies of the nuclear reactions of importance in the formation of the chemical elements in the universe. He got Nobel Prize in Physics in 1983. Some other prominent contemporary researchers in nuclear astrophysics include Alan Koch, Christian Iliadis, R. Seibert, all actively contributing to understanding primordial and stellar nucleosynthesis through experimental and theoretical research. Several Indian scientists are also actively working in this area.
There is no other better position to measure the practicality of any subject except for the active field of its production ground. So, Professor Gupta now explains the relationship with the industry, if there is any.
Now let me conclude about the relationship with industry. Nuclear astrophysics, while primarily a field of academic research, has potential applications in several industries, most notably in the fields of nuclear power generation, nuclear waste management, and material science. Indian industries are also part of the development of state-of-the-art technologies by supplying power converters, ultra-high vacuum chambers, beam stoppers for FAIR experiments in Germany. I would like to conclude by saying a quote from Carl Sagan in Cosmos: "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff."
We are extremely thankful to Professor Dhruba Gupta for sharing a piece of his journey with the listeners and also for sharing his valuable time with us. Thank you so much.